Hello everyone, in this video I'm going to be talking about how ethers react with binary acids such as HI, HBr, and HCl. Out of those three, HI, HBr are actually most efficient because they are more acidic than HCl. HCl is less efficient, and HF, another binary acid but it's not a strong acid, is actually not strong enough to react with ethers. They do require heat, and if you have a primary and secondary ethers, they usually follow SN2 mechanism, and if you have a tertiary, it will follow SN1 mechanism, and I'll show you some examples. Suppose I have this symmetrical ether. The very first step you're going to have in those ethers, obviously, it's a bad leaving group, so you're going to have to protonate the oxygen. So that's why we use a strong acid to protonate the oxygen. So in this case, the lone pair from the oxygen is gonna attack the hydrogen there, and then this is gonna leave to create a lone pair on the iodine here. And then in the process, we're gonna have a protonated ether. So this is an acid-base reaction, and you may see in the books this being written in the reversible form as well, which is completely okay because it's just an acid-base reaction. So I got the hydrogen here now, and this oxygen is going to have a positive charge, and obviously I got the I minus along the line there. Now in the next step, in either way, this is a symmetrical ether, and if I focus on whether this carbon right there or whether this carbon right there, they're both primary carbons. So as a result, this is going to follow an SN2 fashion where I'm going to have this iodide nucleophile attacking this particular carbon. So it doesn't really matter whether it attacks the left carbon or the right carbon because it's a symmetrical ether. And when this attacks here, you're going to have this leaving group leaving like this, and you make, so I'm gonna change the colors there to try to keep color coordination. So I'm gonna have an ethyl iodide here made, and then in the process, the second uh, intermediate right now, wouldn't really say the product yet, is gonna be your ethanol. So it's got an O, and remember this hydrogen was actually was coming from the HI, so I have the color combination intact here. Now this ethyl iodide is obviously one of your products, but this ethanol that you have created doesn't really stop there. So as a result, it's going to get protonated again. So you protonate this alcohol again using HI, and then in the process, you will have now a good leaving group because you don't have a good leaving group when you have an OH there, but now you got a good leaving group once this alcohol is protonated, got a positive charge here. And then in the process, in the next step, you can have this I minus doing the same thing. It's going to do a nucleophilic attack in an SN2 fashion, and this water molecule is going to leave. So you still make this ethyl iodide. So if you have an asymmetrical ether, the alkyl halide that you're going to create are going to be the same at the end of the day. So you're going to make 2 moles of ethyl iodide here. So just draw that right here as your final product. If you have an unsymmetrical ether, then you will make 2 different types of alkyl halides, and I'll show you this in the next example here. So let's look at this particular one where I have unsymmetrical ether, and I'm doing this with an HBr. So like I said, you could do this with an HBr, HI are going to be the most efficient one. So I got HBr. I'm going to use this lone pair here to protonate the ether, and the bond between the hydrogen and bromine breaks. So I'm just going to copy this for the sake of time. I'm going to have the hydrogen here, H plus. Now at this point, you can kind of go ahead and do it a couple of ways. I have this Br minus here, so I can be like, all right, I gotta have this a less sterically hindered position, which is technically going to be this one right there. The left carbon is sterically hindered because of this 3 methyl group. So this bromine is actually going to do an SN2 type attack right here. and then this is gonna go ahead and create a third butyl alcohol. So once you have this third butyl alcohol, this will react again eventually, but let me just go ahead and make that third butyl alcohol. And one of your products is going to be the ethyl bromide here. Now this reaction obviously doesn't really stop here. We're going to have the HBr again, and this alcohol doing the nucleophilic attack or doing another acid-base reaction here. And then you got this protonated tertibutyl alcohol. So I'm just going to go ahead and make a bond here. So now I got a good leaving group. And now since this is a sterically hindered carbon, it doesn't really get attacked by the bromide, but rather it can leave, the water can leave and make a very stable carbocation because it's going to be making a tertiary carbocation. So this is a difference there in the mechanism where if you have a tertiary alcohol or ether, like in this case, you can do this in an SN1 fashion as opposed to if you have a primary and secondary, they usually do an SN2 fashion. So once you have this carbocation created, in the next step, we can have the bromide coming in and doing the nucleophilic attack. And if this was a chiral center, then you have a possibility of making a racemic mixture. But since this is not a chiral center, I don't really have to worry about making the racemic mixtures there. So I'm just going to copy this down here, and we're going to go ahead and put in the BR there. So making it a tertiary alkyl halide, and don't forget your other product that you have made before, that was ethyl bromide. So if you're doing the acid cleaving off this unsymmetrical ether, you will end up making two different types of alkyl halides. If you're doing symmetrical ether, you only make one type of alkyl halide. Now, what's going to be happening if you have suppose an aromatic ether like in this case? Now, aromatic ether is a little bit different in terms of reaction as compared to the aliphatic. So let's just go ahead and do the mechanism here. So I'm just going to be using an HCl here just for the sake of showing different examples. But remember, HCl is not as efficient. It does work. It's not as efficient as if you compare with the HBr and HI. So again, we're going to be doing the protonation first. And once you protonate this, let me just copy this down. So make it a little bit smaller. And we're going to have hydrogen here now with a positive charge on the oxygen. The Cl minus is going to come along and do a nucleophilic attack at this particular carbon here. Because remember, the other carbon is an aromatic carbon. It's not going to do any SN1 or SN2. Aromatics don't do SN1 and SN2. So this is where it's going to be differing from the aliphatic ether. So uh, this chloride attacks at this particular position, and then you complete the electron density on that oxygen, making an aromatic compound here, which is technically going to be the phenol. Let me just take that out. And then you're making an ethyl chloride here. Now, previously what we have done, if this was an aliphatic alcohol, we would protonate this again and have the chloride or halide attacking again and making this eventually another aliphatic, another alkyl halide. But in this case, we cannot do any SN1 or SN2. So no SN1 or SN2 reactions can be taking place on those. So since you can't have any SN1 and SN2 reaction, this is actually going to be your final product. So at the end of the day, you make one aromatic alcohol and you make one alkyl halide whenever you're dealing with these aromatic ethers. As opposed to when you're dealing with these aliphatic ethers, you can make either two types of alkyl halides if you're dealing with unsymmetrical ether. If you're dealing with symmetrical ether, you will make 2 moles of same alkyl halides. So this is all you really need to know about acidic cleavage of ethers. If you have any questions, feel free to leave any comments in the section below.